Today we're talking about Chapter 4, Section 5. And before we do begin, pretty sure this is the second to last full week of class, because we have this week, we have only class on Monday next week, and then we have a full week after Thanksgiving, and then we have finals. So this semester is the end of the semester is quickly approaching. I don't know about you guys, but this semester has definitely flown by for me. Maybe we just do current page. We've never put an example on the title page, have we? Alright, so we're going to start off pretty simple. How about that? We'll start off simple, then we'll get harder as we go, right? Alright, nothing new. But anyways, so an exponential equation is one in which the variable occurs in the exponent. Some exponential equations can be solved by using the fact that exponential functions are one-to-one. This means that if we have some a to the raised to the x power, and that's equal to a raised to the y power, so our bases are the same, then we know that the exponents are going to be equal to one another. We'll use this property in the next example. Alrighty. And realistically, this is super easy. I'm just going to go ahead and snip this because I'm pretty sure it's just going to, it'll fit a lot nicer and neater than if I wrote it. Put a here. Alright, I'll talk about it, but this is definitely the easiest thing we're going to be doing today. So looking at a, if we have 5 raised to the x power is equal to 125, okay, and obviously you can probably do this in your head. You could probably say, oh, that's easy, 5 cubed, right? And you would be correct. But another way to set that up would be to say, you know, raised or rewrite 125 as 5 cubed. And then once we did that, we would have the same basis here, right, 5, and then we would just equate the exponents, which is x is equal to 3. Right. That's a pretty simple one. B is a little bit harder, but again, it's not too much harder, right? So we have the same bases here. Okay, we both the bases are 5. So all we have to do is just simply equate the exponents. 2x is equal to x plus 1, and that's what we see right here. And then we solve for x, which we see to be x is equal to 1. All right. So this is a very I wouldn't say rare example, but it is very simple, and you're not going to have many of these at all because this is abundantly simple. Alrighty, but we'll get to the harder stuff now. Okay. We'll give this its own page. Alright, so the equations in example 1 were solved by comparing exponents. This method is not suitable for solving an equation like 5x equal to 160 because 160 is not easily expressed as a power of base 5. To solve such equations, we take the logarithm of each side and use law 3 of logarithms to bring down the exponents. The following guidelines describe the process. So this is law 3 that we talked about. And what we do here, okay, so if we have log base a, little a, of some a raised to the c power, if you recall, what we do is we take that c, the big C, and put it out front, and that's what we have here. We're going to be using that law to solve our exponential equations, all right? And again, here's a guideline. Of course, we need to isolate the exponential expression. We're going to take logs of both sides, and we're going to solve the variable, okay? Obviously, words mean little to you because you want examples, so let's get to it. Alrighty, so this problem takes logs of both sides, but I'm going to take the natural logs. Okay, so what do I mean by that? Looking down here real quick, down here at these solutions, you see that they're taking the log of both sides. I like to take the natural logs of both sides again because that's just how I've always done things. You'll get the same solution either way, and on top of that, it makes it easier to deal with e's, which we'll see here in a moment. E, of course, being Euler's number, the 2.71828. So I'm going to solve it slightly different from the textbook, but I'm still going to get the same solution. The only slight difference is instead of taking the logs of both sides, I'm taking the natural log. So let's go ahead and start on that. All right, so what I'm going to do is I'm going to rewrite this. Well, actually, first of all, let's ask ourselves, 3 raised to what power will give you 7? Well, we know 3 squared is 9, 3 to the first power is 1, so it's going to be some number between 1 1 and 2, I guess. Well, that's not necessarily true because, I mean, yeah, I guess so. Between 1 and 2, but my variable x has to be something different, right? Because we're adding 2 to it. So it's going to be probably a negative number, right? So that's the thought process here. And what we're going to do is we're going to rewrite this problem. We're going to go ahead and take the natural log of both sides. The natural log of 3x plus 2 is equal to the natural log of 7. Okay, and of course we know this rule. Now, this is a very big important point. Okay, so what I'm going to do is I'm going to take this exponent here, and I'm going to put it in front of the natural log. Okay, and I want you to get into the habit of doing this. We're going to put it into parentheses. Okay, so let's explore if we didn't put it in parentheses. Okay, if we didn't put in parentheses, do you see what we're looking at? We're looking at something that looks like x plus 2 times the natural log of 3. Okay, but that's not the case. The x plus 2 is by itself, right? Because it is the exponent. So get into the habit of whenever you do take the exponent, put it out front, go ahead and put parentheses around it. That way you don't confuse yourself later on. Okay, because doing the arithmetic here is very important, and well, let's get to the arithmetic. Okay, so similar to solving literally any other equation, right? We need to isolate the x. We need to isolate that variable. So what I'm going to do is I'm going to divide both sides by a natural log of 3. So x plus 2 is equal to the natural log of 7 over the natural log of 3. Real quickly, natural log of 7, natural log of 3, the natural logs do not cancel out. That does not make sense, okay? Because the natural log of 7 is a number in itself. It is a number. Same thing with natural log of 3. It is a number. We're saying the natural log of 7. It is not, like ln. We can't just cancel it because we see it. All right. The natural log of 7 is a number in itself. The natural log of 3 is a number in itself. So we can't cancel that. But anyways, we took the natural log of 3 on both sides. We divided the natural log of 3 to both sides. And so hopefully you see why we like to put parentheses here, because otherwise we would have, if that 2 or if that parentheses right here wasn't there, we would probably divide both sides by, or actually it'd be subtracting, right, because it's a plus here. But either way, the arithmetic will be incorrect. Make sure you always put our parentheses out front. Anyways, moving on, since I've rambled enough, we're going to go ahead and subtract 2 from both sides. So we're going to have x is equal to negative 2 plus the natural log of 7 over the natural log of 3, right? And that will give me my solution, which will be, so it's going to be, we said negative 2, wrong button, negative 2 plus the natural log of 7 divided by the natural log of 3. So it's going to be a negative 0. Oh, okay. So this was actually, this is A right here. This is A. Okay. So how can we do that? I guess we can put A up here. Boom. Okay. And then B, we want to use the calculator to find the approximation of the solution around the 6 decimal places. So that would be a negative 0.228774, and then 5/6. Well, that's kind of funny. 5/6 is also the decimal point, but yeah, 5/6 would be the 5th and 6th decimal point. Anyways, that's how we do it. And honestly, it doesn't get much harder than that, right? The hard part, I wouldn't even say, I guess would be memorizing our rules. Okay, so let's go ahead and proceed. And again, see, they used log. The textbook used log, but we see we have the exact same solution, right? Negative 0.228756. Oh, and there's a note. We could use natural log. Alrighty. So solve the equation. I need to isolate that the x. I need to isolate the exponent, right? So what I need to do here is I'm just going to divide both sides by 8. So I'm going to have e raised to 2x power is equal to, well, 20 divided by 8. That's going to be, goes at 16, so 2.5. Right. And then I need to get rid of that e. So how do I get rid of the e? I'm going to take the natural log of both sides. Okay, so I'm going to take the natural log of both sides. So I have natural log of e raised to 2x. That's going to be equal to the natural log of 2.5. Okay. Well, the natural log of 2x. All right. Well, first of all, the natural log of e we know is going to be 1, right? So when we pull that, when we do this, we put this out front. The natural log of e, that's just going to be 1. So it's going to be essentially be 2x times 1. Okay. So it's going to be 2x is equal to the natural log of 2.5. Okay. And then once we do that, we're going to divide both sides by 2. So we're going to have x is equal to the natural log of 2.5 over 2, which is going to be equal to the natural log of 2.5 divided by 2. That's going to be equal to 0.458. Okay. And that's it. Again, all we have to do is just remember our rules, and once we do that, it becomes pretty simple, right? It just becomes moving things around. And again, as I've told you before, in my opinion, that just makes math a lot easier, a lot more fun and entertaining to me. Just moving things around instead of doing mindless computation. This is essentially the same kind of problem. Although it does say graphically, so I'm probably going to have to snip a graph on there. But anyway, solve the equation. We're going to go ahead and take the natural log of both sides, and by taking the natural log of both sides, I know that the left side, and okay, I don't think I really drove the point home last time. So let's do it. Let's drive the point home in this solution, or this particular problem. Okay, so we put the exponent out front. Okay, now I didn't do this on the last example. So if there's some discrepancy, this is why, right? But I really want to drive this point home, which is why I'm doing it this way. Okay. So in the last example, I took this 2x and I put it out front, and then my natural log of e just disappeared, right? It's gone nowhere, right? But if you take your calculator and you take the natural log of e, you will see that you have that the natural log of e, this is equal to 1. Okay, and so that's why we get, well, we have to put in parentheses now, do we? 3 minus 2x is equal to the natural log of 4, right? Because anything times 1 is itself. So I wouldn't say I hand waved that on the previous slide, but you see why that the natural log of e, it just kind of it just goes away, right? Anyways, we're going to go ahead and let's do two things here. Let's just go ahead and add 4 and then divide by -2. So we're going to have, let's see, we can probably do that. Is equal to, we're going to say the natural log of 4 minus 3 all over. And we're dividing by a -2. So it's going to look something like that. All right. And so we will have the natural log .807. Okay, and that's it. And it says solve, and then solve it graphically. So I'm gonna plug this into my calculator. Oh, must be gone. There it is. There we go. Of course, that's solving it graphically, right? I don't know. There's really nothing I can really add to that. I don't like using calculators too often. I would show you how to do it, but kind of limited here, aren't I? I mean, I guess I could go off to Desmos and graph it, but it's really just graphing it, so it's nothing different. Alrighty, so this is a problem you're going to have a problem with. So this might be something slightly different, right? Pretty sure we're taking a short detour here for quadratics, and then we're going to go back to taking natural logs of both sides. But let's first of all examine. Okay, so let's go ahead and not rewrite, but let's try to have a throwback to something we are familiar with. Okay, the quadratic equation. Okay, so the quadratic equation, if we look at the variable here being x, well, again, the middle x is it's just x to the first power, but the first one is exactly the square of it, right? So since it's exactly the square of that first x, then we were able to do something with like a u substitution, right? So we're going to essentially do that here. We're going to make a kind of a u substitution here, okay? So what we're going to say is let's actually examine the problem here. All right, and notice how we have e raised to the 2x power, and it's going to be minus e raised to the first power, or e raised to the x power. Notice how e to the 2x is exactly the square of e to the x. So we're going to make the substitution. We're going to say let e to the x be equal to, we actually don't have to do that here. Let's go and say we'll let equal to u. Okay, we don't have to, but I've already gone this far. So we let e to the x equal to u. Well, if we start with that middle term, then that would be minus u minus 6 is equal to 0. Okay, so hopefully you see that that's what this would be, right? And then of course that first term would just be u squared, right? U squared. Okay. Well, if we were to factor this is pretty easily to factor. It's going to be u, so minus 3 and u plus 2. That's going to be equal to 0. Okay. And then we end up with u is equal to a positive 3 and u is equal to a negative 2. Alrighty. Well, let's now make that substitution again. We're going to let u be equal to e raised to the x power. So let's zoom up here. So that means we have e raised to the x power is going to be equal to 3, and e raised to the x power is going to be equal to a negative 2. Okay. So these are my two solutions, and then I can just proceed from here, right? So the equation e to the x, we're going to take the natural log of both sides. So by taking the natural log of both sides, so again, if I were to do this, I'm going to kind of take the tiny shortcut, but I'm going to show you what I'm doing. I'm going to take the natural log of both of these, okay? And then of course the x comes out front, and then we've seen that the natural log of e's, they are just there once, so they just kind of just stand on the sideline. So realistically, my solutions are simply just going to be, actually I'll put the natural logs there. I'll keep them there. So my solution is just going to be x is going to be equal to 3, and x is going to be equal to negative 2. Okay. However, we do have a slight problem. All right. So, actually, it's going to be not. Oh no. Okay, I messed up. I didn't mess up, but I didn't. I should have just kept it at that. If I take the natural log of both sides, because if I take natural log of the left side, I also have to take natural log of the right side. Okay. So that was a minor error. So this becomes x is going to be equal to the natural log of 3, and then x is going to equal to the natural log of negative 2. Now really quickly, if you were to put well, natural log of 3, it is an actual number, right? I don't know what it is off the top of my head. I didn't actually calculate it. But if we plugged in the natural log of negative 2, right, the natural log of negative 2, and actually we should probably put that in parentheses. Otherwise, well, actually, no. The natural log of, I'm sorry, I'm getting lost. Oh yeah, natural log of negative 2 is an imaginary number. Okay, it does not exist on the on the real number line, right? So therefore, this is not going to be a solution, whereas x equals to the natural log of 3 is going to be the solution. So this particular problem only has one solution, and that solution is the natural log of 3. Okay, hopefully that wasn't too confusing. Let's see. Yeah, only one solution. Alrighty, so next up, so before I proceed here, whenever you get into calculus, you're going to be presented with problems, and unlike this course, college algebra, algebra essentials, you know where you learn a technique, and then you do it a lot after the fact. You learn algebraic technique, and then you do it a lot. Calculus is going to be different. You're going to be given calculus problems, and you're going to have to remember all the different things on how to manipulate the equation that you learned in the classes leading up to calculus. Again, the calculus is not hard. It's the stuff you learned up to it. And a good example would be this particular problem here. All right, so we just got done doing some sort of U substitution, something like that, and we might want to do it here. But the thing is, we don't have to do that. Instead, we can just harp back to what we've learned before, and we see that we can actually, it looks like we can factor out an x e to the x from both terms. Okay, so that's what we're going to do. We're going to factor out x e to the x, and that's going to be, what's going to leave us with 3 plus x, and that's going to be equal to 0. Okay, so hopefully that's pretty easy, right? All right, so if we go ahead and divide both sides by e to the x, well, then we're just going to end up with a simple problem like this, and then it gets pretty easy from there. The solutions are going to be x is equal to 0 and x is equal to a negative 3, and that's it. Pretty easy stuff. But again, matter of fact, that's really easy actually. That doesn't take up much of any time or any space, did it? But we just have to recall what we've done before. That's really it. Okay. All right, now logs. So how do we do logs? We did exponential. Now we're going to do logarithmic. And logarithmic, I dare say, is just as easy. So let's read. A logarithmic equation is one in which a logarithm of a variable occurs. Some logarithmic equations can be solved by using the fact that the logarithmic functions are one-to-one. This means that, similar to what we did with our exponential problem, where we had some number we had some base raised to doesn't matter, and that's equal to some base raised to doesn't matter, we can equate the doesn't matters, right? So we can use that same idea with logarithms. Right? So this is the logarithmic equivalent of example 1. Okay, so first of all, let's go ahead and rewrite this. So let's rewrite the left side. We don't have to rewrite it, right? We're just gonna lost my O there. Log of x squared plus 1, that's equal to. Now the right side, what I'm going to do here is I'm going to go ahead and rewrite it as one logarithm, right? That one logarithm would be, we're just going to do some head math here. It's going to be x squared, and it's going to be plus 3x, and minus 2x is going to be plus x, and then minus 6. Okay, because again, if you recall, if we're looking here, if we are adding two logarithms together, then what you do is you multiply their arguments together. So I just basically did x minus 2 and x plus 3. I did that to get x squared plus x minus 6. Okay, and then from here, all we have to do is equate my arguments. So I'm going to have x squared plus 1. It's going to be equal to x squared plus x minus 6. Right? So this looks pretty easy. The x squared is going to cancel, and I'm going to go ahead and add 6 to both sides, so I have x equal to 7. Okay. And 7 does work in my original equation, because if I plug it in 7 into any of these x values, right? 7 squared is 49, 49 plus 1 is 50, that's positive. 7 minus 2 is 5, that's positive. And 7 plus 3 is 10, and that's positive. Okay, so 7 does indeed work. And before I can proceed, yeah, those are okay. All right, and that's it. Okay, so more guidelines, and I guess I'll snip that with the actual example. So we're gliding right along. 25 minutes, we're on example 8, right? So this is pretty easy stuff. So same thing, we're going to isolate the logarithmic term on one side. We need to write the equation in exponential form. We don't have to, but it helps for some, and we'll see that. And we're going to solve each equation for x, okay? So a, the natural log of x is equal to 8. So what we can do here is we can, in order to get rid of that natural log of x, actually, no, we'll just do that. Okay, so what we're going to do for a, we'll put a up here. So this is another reason why I like to raise or use e's, right? What we're going to do is we're going to raise both sides to the e power. What I mean by that is I'm going to put it's going to be e raised to the natural log of x, and that's going to be equal to e to the 8th power. Okay, all I did was basically I just raised both of these sides to the e power. Right? So as long as I do something to one side, I do it to the other, I'm good to go. Okay. So once I get to that point, well, I know that I can, I can use my normal rules here, where what is it called? My power. I don't forget what it's called. Where I put that x out front, and then I've got e raised to the natural log, which is also just going to be 1. So I have x is equal to e to the 8th power, and that's it, right? E to the 8th power, whatever that may be. So that's it for A. B, all right, so B is a really good one. So if we have, this is definitely an example of you might be going autopilot. Okay, we have log base 2 of 25 minus x is equal to 3. All right, so you're thinking, oh, what do I do here, right? But if you recall, that I can rewrite logarithms in exponential form, right? Well, my base is 2. Okay, 2 raised to the what power? Well, that's 3, which is the other side. And that's going to be equal to my argument, 25 minus x. Okay, that just goes back to what we've done before, where log base a of x is equal to y is the same thing as a raised to the y power is equal to x. Okay, one of the very first things we did concerning the relationship between logarithms and exponents. So once I reduced it down to this, well, then it becomes pretty easy, right? Well, 2 cubed is 8, so I've got 8 is equal to 25 minus x, and I honestly should put that. Let's go long ways here. 8 is equal to 25 minus x. If I subtract 25 from both sides, I end up with, let's go and put the negative x on the left side. So negative x is equal to, I subtract 25 from both sides, so that's going to be what, negative, shoot, I just went dumb, 17. So, all right, and then if I actually solve for x, I end up getting a positive 17. So x is equal to 17. Okay, and then we can, just kind of eyeball it, right? Eyeball check it. Well, 25 minus 17, well, that's 8, and natural log of 8, or the log base 2 of 8 is some number, right? As long as, like, let's say this was a negative 26. If this was a negative 26, and I plugged in a negative 26 there, actually that wouldn't make sense either. Negative 26 does work. If it was a positive 26, if I put a positive 26 into there, well, 25 minus 26 is negative 1, and that does not exist in the domain of logarithms, right? We cannot have a negative number. So that's how that works. But 17 works, right? 25 minus 17 is 8. We're good to go. Okay, so more kind of autopilot-y problems here. First, again, we need to isolate that logarithm. So we're going to subtract 4 from both sides. So we're going to have 3 log of 2x. That's going to be equal to 12. We're going to divide both sides by 3. So we're going to have log of 2x is equal to 4. Okay, well, what do we do here? Well, we have log of 2x equal to 4. So if you recall, log has that implied base of 10, right? So this would just be simply saying 10 raised to the 4th power is equal to 2x. Okay. Well, 10 raised to the 4th power, it's a 1 with 4 zeros, right? So that becomes 1 to 4 zeros, so it's going to be 1 and then 1, 2, 3, 4. 10,000, put a little comma there, is equal to 2x, and therefore we see that x is equal to 5,000, right? And of course, x equal 5,000 is more than okay, because if we put a 5,000 in for x, well, that's log of 10,000, so and that's okay, right? So that's what happens when we have a logarithm. We have to remember that if it's just a log with no base, with no base that's shown, then we have that implied base of 10. Implied base of 10. All right, so solve the equation. So again, we're going to hopefully when we started this chapter, I said, chapter 3 was the hard one. Chapter 3 is the one that gets us the most trouble. Chapter 4, you basically just kind of move things around to figure things out, and hopefully you're seeing why that is now, right? So anyways, the left side, we have an addition sign there, so we're going to multiply the arguments with one another. So we're going to have log of, right, and it's going to be x squared, and then what? Negative x and a plus 2x, so it's going to be plus x, and it's going to be minus 2. That's going to be equal to 1. Alrighty, and then same as before, what we need to do is we need to recall that this is a base 10. So this is the same thing as saying 10 to the first power. That's easy. 10 to the first power is just 10. 10 is equal to x squared plus x minus 2. Let's subtract 10 from both sides. And so I'm going to go ahead and flip everything over, because I like to have my 0 on the right. You probably do too. So it's going to end up being x squared plus x. And I said I subtract 10 from both sides. So we're going to have minus 12. This is going to be equal to 0. Alright, so now I need to factor. It looks like it factors into a pretty easy 4 and a 3. So x looks like plus 4. X minus 3 is equal to 0. And therefore I have x's at x is equal to a negative, let's do positive 3, no, let's do negative 4. At negative 4, and x is equal to a positive 3. Okay, we're not done though, because we're going to plug these in. So if I plug in a negative 4, okay, well, negative 4 plus 2 is a negative 2. I mean, I can stop right there. I can't have a log of negative 2. So this tells me right away that negative 4 is not a solution. Okay, and then x equals to 3. Well, 3 plus 2 is 5. 3 minus 1 is 2. So x equals 3 is okay. Right? Now, before we proceed, I do have students thinking, okay, well, this is x equals negative 4. All right, it's a negative number, therefore it's not going to be in the domain. And that's not true. That's not true, right? It could just as well have been, if this was log of, let's see, x plus 10. If it was log of x plus 10, well, if I plugged in a negative 4 right here, well, negative 4 plus 10 is a 6, and log of 6 does exist, okay? Just because my solution is negative does not mean that it is not part of the solution, okay? Furthermore, just because it is positive does not mean it's part of the solution, and we saw that on this example, right? If x was equal to, let's go ahead and say it, if x is equal to 30, Okay, well, if I plug a 30 in right here, 25 minus 30, that's negative 5. Okay, so you must plug those values in, but at the same time, they're pretty easy. Like you don't have to actually solve for x. You don't have to do anything like that. Just plug the value in into the argument, and if it's positive, you're good to go. If it's negative, you're not. If it's 0, what are you? You're also not good to go, right? Because we can't have the natural log of 0. Okay. And then the last one for the day. Oh, we have to solve it graphically. Okay. Well, again, graphically, we just use our calculator. And I'll go ahead and give this its own slide. I'm pretty sure I can't fit it. Yeah. Okay, so let's put an example 10 on that. There we go. Okay, now we can proceed to the last one. This is also graphically. Okay, well, this makes the end of the lecture easy. So where we got? Then we graph. So yeah, that's it, guys. You just put it into your calculator. Again, though, I don't have calculator problems when it comes to my exams or graphing things like this, where you need a graphing calculator. Because, well, first of all, graphing calculators are very expensive. Secondly, you can't use your cell phones, so we don't do much of that. But I do want to show it because I want you to see the relationship, I suppose, right? Anyways, that does conclude today's lecture.